Today we are going to solve this equation x raised to power 5 plus 1 equal to 0. So we'll move this plus 1 to the right hand side. This will become x raised to power 5 equal to minus 1. And when we look at this equation, can we think of any number which when raised to power 5 equal to minus 1? So the only number which comes to mind is minus 1. Minus 1 raised to power 5 is equal to minus 1. Other than that, we can't think of any number which when raised to power 5 is equal to minus 1. I'm talking about real numbers. So if you look at this equation, this equation has degree 5. So that means that it must have 5 roots. So we can only think of one. So what does it mean? It means that it has only one real solution. That doesn't mean that it has one solution. It has 5 solutions and only one real solution. The remaining 4 will be complex. So we also need to find those complex solutions or roots, I should say. So we are interested in x, and x has power 5. So we'll be taking fifth root on both sides. So this becomes x5 raised to power 1 by 5 equal to minus 1 raised to power 1 by 5. Power and power get multiplied, so 5 and 5 cancel out each other. So we are left with x is equal to minus 1 raised to power 1 by 5. So we are seeing that x is equal to minus 1 raised to power 1 by 5. Now how can we solve this thing? So we are looking to find complex numbers, which are the solution of this equation. So we need to write it in the form of a complex number. So complex number has multiple forms in which it can be written or represented. So one of the forms of complex numbers is polar form. So polar form is basically it comes from your basic form of a complex number, which is the Cartesian form x plus iota y. And when we use some trigonometry, we end up with the polar form if we take a complex number and on a unit circle. So we end up with x having value r cos theta, where r is our modulus of the complex number, and y becomes cos theta. So the polar form becomes r cos theta plus r iota sin theta, where r is the modulus of a complex number and theta is the angle of a complex number. So this is basically what I want to do is write this minus 1 in the form of a complex number, and that too in polar form of a complex number. So that means there will be cosine, there will be sine, and we have to take the angle in such a way that this whole thing becomes equal to minus 1. So if you draw an Argand diagram in which x-axis represent the real part of the complex number and y-axis represent the imaginary part of a complex number. So we have minus 1. So minus 1 doesn't have the imaginary part. So it only has real part. So it will be on negative side of the x-axis. And if you look at this minus 1, what angle does this have from the positive x-axis? So the angle is basically 180 degrees. But as we know that cosine and sine, their values repeat. So as this complex number is present on x-axis, this will only have the cosine part, not the sine part, because the imaginary part is missing. So cosine of the angle must be equal to -1. But we can't really write cosine of pi, because cosine can have the value of -1 at multiple angles, not just pi, but pi plus, any multiple of 2 pi, because cosine is periodic and its value repeats after every 2 pi radians. So this angle is pi 180 degrees. We'll talk about only radians here because of a reason, which I'll explain or later. So the angle cosine will have value, or this -1 equal to -1 at pi plus another 2 pi, meaning it will have the value -1 at 3 pi, and 3 pi plus 2 pi 5 pi, and so on. So we need to write cosine of pi plus 2n pi, and when we put values of n here, if we put 0, we'll end up with cos of pi, which is -1. If we put 1, we'll end up with 3 pi. Cosine of 3 pi is again -1, and so on. Similarly, if we put 0, we'll end up with sine of pi, which is 0. Again, if we put 1, we'll end up with 3 pi. Sine of 3 pi is again 0, and so on. So this part will keep getting equal to 0, and this part will keep giving us answer of -1. So we can write this -1 as this thing. But the polar form of a complex number is r cos theta plus r iota sine theta, where r is the modulus of the complex number. So here the number was -1. It only had x part, real part, which was -1. So to find the modulus of a complex number, we need to add the squares of its real and imaginary parts, and then take the square root of that answer. So here we only have -1, the real part. So -1 squared is 1, and square root of 1 is 1, and modulus is basically the length from the origin of that complex number. So here you can see from origin this -1 has length 1, so modulus is just 1. So if you multiply it by cosine this thing or sine this thing will be unchanged. So the modulus doesn't play a part in this thing, so we'll end up with this polar form. So we have established that we can find the values of x by this thing, and we know that there will be 5 roots, 5 answers, and for that we need to put the values of n here, and we'll put the values of n from 0 till firstly we need to this is not basically our final answer. Firstly, we need to establish that this thing, cosine of theta plus iota sine theta raised to power 1 by 5, is basically we can apply De Moivre's theorem here, and De Moivre's theorem states that whenever we have cos theta plus iota sine theta raised to some power, it can be written as cos of n theta, meaning this power multiplied by this angle. So we'll end up with cos of 2n pi plus pi over 5 plus iota sine of the same angle. So this is the final answer, and we'll just put values from 0, 1, 2, 3 up till 4, because we are interested, or this equation has only 5 roots. If we put the values of n any further, we won't be getting any different roots. Those roots, those roots will be same as these, the roots coming from these numbers, putting these numbers. So we need to establish some things before putting the values and finding the final roots. And firstly, we in order to find the solution for this equation, we use De Moivre's theorem. So we need to establish that De Moivre's theorem is indeed true. For that, we consider a complex number on the unit circle, and we'll consider its exponential form. So uh, a complex number can be represented in three forms. First form is Cartesian form, which is x plus iota y, where x is the real part, y is the imaginary part. Second is the polar form, which is r cos theta plus iota r sine theta, where r is the modulus and or the distance from the origin of that complex number. It is a length basically, and theta is the angle that complex number makes with the positive x-axis. And the third is this exponential form, e raised to power iota theta. And theta is basically the angle which the complex number makes with the positive x-axis, and r is your modulus. Here r is not present because I've considered a complex number which is on a unit circle, and unit circle means that it has radius 1. So this is the complex number z, and it is on the unit circle. It has the real part of x and the imaginary part of y, and the angle is theta with positive x-axis, and the modulus is 1 because the modulus is the length of the complex number from the origin, which is 1 in this case because this is a unit circle. So the exponential form is r e iota theta, where r is the modulus. Here the modulus is just 1, so this becomes e raised to power iota theta. And this thing is equal to cos theta plus iota sine theta. What I'm saying is that the polar form of a complex number is basically equal to its exponential form. Like, these two are the same things, just written in a different way. They're just representations of a same thing, of this z. And we need to prove it first, and then we can use this thing to prove De Moivre's theorem. So what we want to prove here is that e raised to power iota theta is equal to cos theta plus iota sine theta. And for that, we use the power series for e raised to power x, and the power series for e raised to power x is simply x to the power 0 over 0 factorial plus x to the power 1 over 1 factorial plus x square over 2 factorial plus x cube over 3 factorial, and this goes on and on. So e raised to power x is equal to x raised to power 0 is 1, 1 over 0 factorial is 1, plus x raised to power 1 is 1, 1 factorial is 1, x square is x square, and 2 factorial is 2, x cube over 3 factorial. So factorial is basically the number whose factorial you are interested in. You basically start multiplying from that number till 1, and you go in the reverse direction. So if you are interested in the factorial for 3, you will basically find 3 multiplied by 2 multiplied by 1, which is 6. So this is the power series for the e raised to power x. And how does this series help us, or what is the purpose of this series? It's basically finds the value for e raised to power anything. You can put x equal to anything in this series, and this series will simply calculate the value for that power of e by simply putting that number in this series and adding. So the final answer is e raised to power x is equal to 1 plus x square over 2 plus x cube over 6 plus up to so on. So we now have the series for e raised to power x, and we are interested in finding e raised to power iota theta. We want to put x is equal to iota theta, and want to see that whether this comes equal to cos theta plus iota sin theta or not. So we are using x is equal to iota theta. So when you put iota theta in place of x, you end up with 1 plus iota theta whole squared over 2 plus iota theta whole cube over 6 plus iota theta whole power 4 over 24. And e raised to power iota theta, when you simplify this right hand side, you end up with 1 plus iota square over 2 plus iota cube theta cube over 6 plus iota 4 theta 4 over 24 up to so on. And when you put values for iota square, iota cube, iota 4, iota square has value -1 because iota is equal to square root of -1. Iota cube is equal to iota square times iota, so iota square is -1, so -1 times iota is simply minus iota. Iota 4 is equal to iota square whole squared, and iota square is -1, so -1 whole squared is equal to 1. When you simplify, you end up with 1 plus iota theta minus theta square over 2 minus iota theta cube over 6 plus theta 4 over 24 up to so on. So when you separate the real terms and the imaginary terms in this series, the real terms are 1 minus theta square over 2 plus theta 4 over 24 up to so on, because we have only put the values we have only calculated or added the first 5 terms, but the series keeps going on and on. It doesn't end here. So that's why these real terms will also not end, and we'll take iota common from the imaginary terms, and the series in this bracket also, this keeps going on and on. So theta minus theta cube over 6 plus up to so on. The signs are alternated, and here we also have the alternate signs in consecutive terms. So this basically is the series for cos theta. So the power series for cos theta is this, and this is with the even powers of theta raised to power 0 is 1, theta squared, theta 4 up to so on. And similarly in the denominator we have the factorials for the even numbers: 0 factorial which is 1, 2 factorial which is 2, 4 factorial which is 24, and so on. In this bracket we have the power series for the sine, and we have odd powers: theta 1, theta cube, theta 5 up to so on. So this is the power series for sine. So e raised to power iota theta is equal to cos theta plus iota sine theta, and this is what we were looking for. So we have proved that e raised to power iota theta is equal to this thing. Now we need to prove de Moivre's theorem. So e raised to power iota theta is equal to cos theta plus iota sine theta, but if you remember, we used cos theta plus iota sine theta raised to some power. So we need to raise that cos theta plus iota sine theta to a power n in order to prove for de Moivre's theorem. So we need to raise this complex number to power n. So z raised to power n is equal to e raised to power iota theta raised to power n, and power and power get multiplied, so you will end up with e raised to power iota n theta. So if you look here the theta angle was theta, here the angle is n theta, so this same rule will be applied, but in place of theta, n theta will be there. So cos of theta becomes cos n theta plus iota sine n theta, and this is indeed our de Moivre's theorem. So we have established that De Moivre's theorem is indeed correct and indeed true. And now we need to put those values of n in our final solution to find our roots. And here is that final solution, and we'll just put values for n 0 till 4 in this equation and get our roots. So putting n is equal to 0 in that equation, we get cos of 2 times 0 times pi plus pi over 5 plus iota sine the same thing, sine of same thing. So we end up with x1 is equal to cos of 0 plus pi over 5 plus iota sine 0 plus pi over 5 cos pi over 5 plus iota sine pi over 5. Cos pi over 5 is 0.809 plus 0.587 iota. One thing which I wanted to tell you earlier is that the power series which we used to prove De Moivre's theorem, that is basically only applicable on the angle in radians. So that's why we are dealing with radians here. So x1, the first root for this equation is this, and this is a complex number. It has real part and an imaginary part. So by putting n is equal to 1, just need to simplify it. Simple enough. So x2 is equal to x2 is minus 0.309 plus 0.951 iota. So we have the second root for our equation. And when we put n is equal to 2, we end up with cos of 5 pi over 5 plus iota sine of same angle. 5 and 5 cancel out. We end up with x3 is equal to cos pi plus iota sine pi, which is cos pi is minus 1 and sine pi is 0. So minus 1 plus iota times 0. So this becomes equal to minus 1 because 0 times anything is equal to 0. So this was the first solution which we could easily think of because it is real. So this is our third solution or third root for this equation, and it is x3 equal to minus 1. x4 is calculated by putting n is equal to 3. It is equal to minus 0.309 minus 0.951 iota, and n is equal to 4 gives us 0.809 minus 0.587 iota, and this is our final root. So we have found all the roots. Now we need to verify that whether if we put any further values of n, whether we get different solutions or not. We should have we should have the same solutions because the number of roots should be 5, as the degree of the equation is 5. So when we put n is equal to 5, we end up with 0.809 plus 0.587 iota, which is the first solution, or the same as x1. Similarly, when we put n is equal to 6, we end up with x7 minus 0, which is minus 0.309 plus 0.951 iota, which is same as x2, our second root. So that means that the solutions or the roots have started repeating. So this basically tells us that we don't need to further put any value of n in that solution because we won't be getting any distinct solution. So these 5 are the roots. But actually there are two more things I need to tell you, that firstly, the complex numbers or the roots, the complex numbers which are roots of an equation are always in the form of complex conjugates, and they are in pairs, and they are in pairs of complex conjugates whenever the coefficients of our equation are real. So we had the equation x5 plus 1 equal to 0, and the coefficients are just 1 and 1, which are real. So that means that the complex roots for our solution, the complex roots for our equation will be in the form of pairs, and they'll be in the form of complex conjugates. So this x1 is 0.809 plus 0.587 iota. This is same as our x, sorry, not same, but the conjugate of our x5. And our x5 was this. This was our x5, and this simply has just the opposite sign with the same imaginary term. So the sign of imaginary term in this number has changed. So that means x1 and x5 are complex conjugates. And similarly, x4 is minus 0.309 minus 0.951 iota, and x1 is the complex conjugate of the same thing. So that is all.